So in the beginning of this set of slides, we talked a little bit about concentration units, and I think essentially I told you at some point we're going to want to introduce a concentration unit so we can talk about how much stuff there actually is in a given solution, but also we want a concentration unit that's going to be effective for communicating with a balanced equation. So with that idea in mind, that's where we're going to introduce the concept of molarity. And there are a lot of different ways to measure solution concentration. In the very last set of slides, I'll talk about a couple other options, I think. But mostly what we're going to be interested in talking about is molarity. And molarity is always going to be defined as moles of solute in the numerator, so whatever it is we're dissolving into our solution, and then volume of the total solution in liters in the denominator. So it's always going to be in terms of moles per liter. So having it in terms of moles is really important, right? Because molecules or moles, that's what we're communicating in balanced equations. So this will make it a lot easier to link our information to a balanced equation. And then the volume unit of liters, that's just, we need to be aware that that's what it's always going to be in terms of. So this will just be a way to tell us for a given amount of solution how much solute we're actually expecting to find. For us, the solution is always going to be solute dissolved in water as the solvent, but in theory this could apply to other situations as well. So very briefly, we'll think about kind of conceptually how you would actually go about making a solution up in the lab, and then start to think about some calculations that we could have related to that. So imagine that you want to make a solution of a particular molarity. So from that molarity, you would convert moles into grams using the molar mass of whatever substance it is, and then that would tell you the amount to weigh out. And so that would match up with whatever number of moles you have, and then you'd add the solute to the volumetric flask, whatever it may be. So this is describing if the solute were a solid, which is what we want to start with. Then in practice, essentially, after adding the solute, you kind of cover it in water, swirl it around until the solid dissolves, and then you add solvent to the line at the top of the volumetric flask. So that's what we want to think about there. And so this is just showing that same idea, right? Add solid, cover it with liquid, swirl it around till it dissolves, and then fill it up until you reach that meniscus where you reach that line where your meniscus, let's see, what color can I use that'll show? Here's your meniscus here, right? It's going to dip down a little bit with water filling this narrow passage, and we want the bottom of the meniscus to be touching whatever the mark is on our volumetric flask. Okay, so let's look at a worked out example, and then we'll work through a few of these as well. And it says, what mass of potassium iodide is required to make 500 milliliters of a 2.80 molar potassium iodide solution? So the question is asking, what mass of potassium iodide? So we still want to try to think about this in terms of a conversion type problem. So with that idea in mind, starting with our volume value, which is typically going to be in milliliters, we want to convert into a number of moles. So generally speaking, it's going to be milliliters to liters first, and then to moles. And the way I'm going to get to moles is by using the molarity value, right? If I multiply the volume in liters by the molarity, that'll change me out from liters and into moles. Then, if I want to change moles to grams, then I'd use the molecular weight, that's what MW is, or molar mass, MM, either way is fine, to convert from moles to grams. So that's what you see in our example down here. In step 1, we're converting milliliters to liters. And then in step 2, it's liters to moles. And then in step 3, it's moles to grams. So remember, molarity is moles per liter. So if I multiply a value in molarity by a volume in liters, that'll just leave me with moles. So when we follow this calculation across 500 milliliters, I convert it into liters by dividing by 1,000 milliliters. Then I'm in liters. I multiply by the molarity to get out of liters and into moles. And then in the last step, I go from moles to grams. So when I'm all done, I have grams left. This is an example I took from somewhere else, so they're doing their significant figures slightly differently, but they end up with their answer, 232 grams of potassium iodide. Okay, so hopefully that makes reasonable sense, and this is the most common question that we really have to answer in molarity calculations, where we're just saying, how do I prepare a solution of a given molarity from a solid solute? So this first question of these two is exactly like what we just did, but there's another question that kind of really ends up just being a conversion type problem, where we're given the concentration in terms of grams and milliliters, and we need to change it into moles per liter. Okay, so usual plan, pause it if you want to work on these on your own, otherwise I'll just keep going here. So in this first one, I want to make 255 milliliters of a 1.50 molar sodium chloride solution. So it's important that I know that it's sodium chloride, right, because I'm going to need that molar mass. And then in terms of what they're specifically asking us, it's what mass of sodium chloride. So if we go back for a second, right, I went from volume of solution to moles to grams. So we can kind of follow that exact same plan here. Let me write that down. We're going to go volume to moles to grams. All right, so I have 255 milliliters times 1 liter over 1,000 milliliters, and I'm just duplicating what they did, or what I did in the above example. You can start with liters if you want to, but if I'm just following what we did there, that's our first step. And then now molarity makes sense, right? Because it will be 1.50 moles sodium chloride per 1 liter. So we're off to a good start here, right? Milliliters cancel with milliliters, liters cancel with liters, and now I'm in moles, but I want to be in grams. If we calculate the molar mass for sodium chloride, we've done this one a few times. It should be 22.99 for sodium and 35.45 for chlorine, so we'll get 58.44 grams of sodium chloride. So moles cancel moles, we're left with grams. Let's see, we can solve that real quick. Uh, 22.4 is what I get to 3 significant figures. So that means that we're going to dissolve, so we'll add 22.4 grams to whatever our container is, add enough liquid to cover and dissolve it, and then top off our container to get our 255 milliliters total volume. And just a side note, right, the difference between the total volume and the amount of water we're going to add, theoretically those aren't going to be exactly the same, but we're going to treat them as if they are. So then the other question, like I said, is more of a conversion problem where we know information about our solution, just not in terms of moles and liters, so we'll want to figure out how to switch it to that. So what I have is a solution that is 55.6 grams of sodium hydroxide in 388 milliliters water. And this is what I was kind of talking about. The total solution volume and the amount of water that there is, we're going to use those interchangeably, even though that may not exactly be the case. So I can set this up as a one-line conversion if I want to, or I can just independently convert grams to moles and milliliters to liters, and that's totally up to you. This time I'll set it up as a conversion. We do need to know the molar mass of sodium hydroxide, so let's start by doing that. So that should be 22.99 for sodium plus 16.00 for oxygen and 1.01 for the hydrogen. Looks like that should be 40 exactly, right? So 40.00 grams per mole. Okay, so I have grams per milliliter and I want to change it into moles per liter. So 55.6 grams sodium hydroxide per 388 milliliters. So we'll change the grams to moles in the first step. 1 mole sodium hydroxide per 40.00 grams sodium hydroxide. So grams cancel grams, and I'm in moles per milliliter, which isn't quite right. So now 1,000 milliliters per 1 liter. Milliliters go with milliliters, and I have moles in the numerator, liters in the denominator, so that looks like the way we want to do it. So again, I'm showing you a conversion including the actual conversion from milliliters to liters. If you just want to move the decimal and save that step, of course, that's totally okay. In that case, this really wouldn't be a one-line conversion. You just change grams to moles and that's it. Okay, 55.6 divided by 388 divided by 40 times 1,000. And to three significant figures, this is 3.58 molar. What is it? NaOH. So that makes fairly good sense, right? We know 1 mole is 40 grams, but we have 55 grams, so that's substantially more than 1 mole, and it's only in about 400 milliliters of water, so 3.58 ballpark seems like a reasonable answer. It's a little trickier to guess if this one makes good sense in this particular case, but that's kind of, I just look at it to make sure it's relatively reasonable as we're considering these problems. Okay, so those are really the two main types of problems that initially come up when we're thinking about molarity calculations. But if you think about what we were doing here, this was dissolving a solid into water to get a particular concentration. And that happens an awful lot, but there are also times where I already have a stock solution and I want to dilute it to a new concentration, whatever it may be. Like for acids in particular, right, we buy hydrochloric acid as a 12 molar solution or sulfuric acid as an 18 molar solution, and then we dilute it down to whatever it is we want to actually use in the lab. Okay, so the picture here, the set of pictures here, it's basically describing that I have a stock solution on the right, and I'm transferring some of that stock solution to the left, and then diluting it with water to a new concentration. So in lab, we would use a pipette to pull however much we need out of the stock bottle, transfer it to our new volumetric flask of whatever desired volume, and take however much we think we need, and then fill it up with water to the mark. So let's say, just for argument's sake, that I have one, oops, I'm never going to stop doing that, I guess. Let's just say I have 1 molar in my stock bottle, and I transfer, let's say, 50 milliliters into my new container, and then I top it off with water to 100 total. I don't think that's what the picture is describing. Let's say, for argument's sake, that's what we're doing. Then if I were to do that, if the original solution is 1 molar, that would make the new solution 0.5 molar, right? I took half the volume over, so at that time when I just transfer it, they're both 1 molar solutions. But then when I fill up the remaining half of the container with water, then the new molarity is going to be 0.5 molar. So in all of that description, right, we didn't even talk about moles, right? That would be true of any concentration unit. So as long as I'm kind of tracking my initial amounts and my final amounts, then I should be able to talk about what the new molarity is going to be. So here's the key idea in terms of what we're thinking about. I'm going to take some amount of solute from my stock bottle, the highly concentrated one, to my new container. And then I'm just going to add water to it. So whatever number of moles I initially transfer to the new container, that's going to be a constant throughout. All that's going to change is the total volume. So with that idea in mind, we'd say moles before dilution equal moles of solute after dilution. And remember with our equation, right, molarity equals moles per liter. But then that means molarity times liters equals moles. Or in general, molarity times volume equals moles. So then this equation down below, it can get written a couple of different ways. I usually write it as M1V1 equals M2V2. The molarity of solution 1 times the volume of solution 1 equals the molarity of solution 2, volume of solution 2. You may also see it written as MAVI for molarity initial, volume initial, equals molarity final, volume final. Same difference in terms of how we're going to use it. So essentially it leaves us with a 4-parameter equation, and then we just want to solve for whatever it is that is the missing information. So we'll look at a few different examples of how to apply this equation. Okay, so here the question says, how would you prepare 60 milliliters of 0.2 molar HNO3 nitric acid from a stock solution of 4 molar nitric acid? So we should immediately recognize that it's an M1V1 equals M2V2 problem because it's asking you about a particular solution and telling you about the stock bottle concentration. So pretty much as soon as my problem shows up with more than one concentration, I'm already thinking that I'm going to use M1V1 equals M2V2. So really my job here is to figure out what I know and what I need to know. So the given information is about the solution that I want to prepare. So that'll be my final solution, right? That'll be what I'm trying to make. So with that in mind, M2 is going to be 0.200 molar. And for mathematical accuracy, in theory, I should change my volumes to liters. But what you're going to see is it's all going to cancel out anyway. So as long as I'm consistent with my volume units, that's all that really matters. And then I know the stock bottle is 4 molar. What I don't know is how much I'm going to take out. So let me go back for a second, right? Basically what we're trying to solve for is how much I'm going to take from the stock bottle and transfer into the new container. And that's V1. So if M1 V1 equals M2 V2, if we solve for V1, I'm just going to divide both sides by M1, so I get V1 equals M2 V2 over M1. And so that's what I'm going to set up. And I have all the values I need here, right? Here's M2, here's V2, and then here's M1. And when I solve for that, I get my answer of 0.00300 liters, trying to keep my significant figures consistent, 3 in all of our values. Then when I convert it into milliliters, I'll get 3 milliliters. So again, to be mathematically correct, in theory, every time I work with molarity, I should use volumes in liters. But like I said, the units are going to cancel out in M1 V1 equals M2 V2. So if I happen to use milliliters, that's okay. I just need to understand that if I put milliliters in, then all of my volume units that come out of it are also going to be in milliliters. Okay, so we got some number out of this, right? 3 milliliters. But the question is, how would you prepare 60 milliliters of 0.2 molar nitric acid from a stock solution of 4 molar nitric acid? So what does that 3 tell me? The 3 tells me that I'm going to need 3 milliliters of the acid combined with however much water I need to reach the desired total volume of 60 milliliters. So I guess 3 milliliters of acid and 57 milliliters of water is going to get us to our target volume. So that's what we would do in this particular case. In practice, you add acid to water. So probably you'd add a little bit of water to your container first, then add your 3 milliliters of acid and then swirl it and then top it off with the remaining water. At a low concentration probably doesn't matter, but in theory that's the correct way to do it. Okay, I think I have 3 more problems in this, working with this equation, and that'll be it for this video. All right, so this next one, pretty similar to what we just did. How would you prepare 225 milliliters of 0.5 molar HCl from a stock solution of 6 molar HCl? So same idea here, right? We're going to use M1 V1 equals M2 V2. And again, the question is how much do I need to get out of the stock bottle? So I'm solving for V1. So it'll be the same equation as before, isolating for V1. So let's see. M1, oops, not MI. M1 is 6 molar. V1, we don't know. M2 is 0.5 molar. V2 is 225 milliliters. So if I now isolate for V1, right, V1 equals M2 V2 over M1, I have all the values I need to plug in, right? 0.500 molar, 225 milliliters, and then 6 molar. So now I went directly in with milliliters, and my rationale for that, like I was saying earlier, is in this equation, the molarities are going to cancel. So whatever units I put in for volume, those are the ones that are going to stick around. Okay, so 0.5 times 225 divided by 6. 18.75 is what I got. Let me write that down. But if we apply the odd-even rule in this case, then 7 is odd, just ending with a 5 and nothing else. 7 is the cutoff number, so we'd call it 18.8 milliliters in this case. Okay, so hopefully here you're seeing why I was telling you it's okay to go into this with milliliters. Just understand your answer will also come out in milliliters, which is typically fine. That's what we want to be able to do. Okay, 2 more example problems, a little bit different, but same kind of idea. Okay, so what's going on here? We start with 25 milliliters of 0.8 molar HCl, and then we add 25 milliliters of water. So what we're doing is doubling the volume. So if you think about the equation M1 V1 equals M2 V2, if I double the volume, the molarity should become half as much, right? If I'm adding water to dilute it, the molarity will go down. If I'm doubling the volume, 25 plus adding a new 25, then the new molarity should be half the original molarity. So without doing any math, I should look at this and say I'm going to get 0.40 molar. But let's walk through the process to make sure we see where everything goes. And then the next problem is the same type, but just not round numbers, so we'll actually have to work it all out. So the question is, what is the new molarity of the HCl solution? So I'm trying to solve for M2. After dilution, what do I get? So let's write out what we know. M1, I'm going to keep doing that. M1 is 0.80 molar. V1 is 25 milliliters. M2 is, we don't know yet, and V2 is 25 plus 25, so it's 50 milliliters, a dot just to indicate 2 significant figures. Okay, so here we go, right? M2 is what I'm solving for, so that's M1 V1 over V2, all of which I have. So 0.80 molar. V1 in milliliters, that's okay because I'm also going to put V2 in milliliters. So now milliliters cancel milliliters and we're left with molarity, which is what we want it to be. And of course, when I do that calculation, I get 0.40 molar. So an important thing here, right, is I added 25 milliliters, right? The new volume is the original 25 plus the 25 that I've added. So that's something that I want to keep track of. Okay, so let's do the next one of these. Same exact type of problem, just different numbers. So let's see. Start with 35 milliliters of 0.64 molar KOH, potassium hydroxide, and add 15 milliliters of water. And what is the new molarity of the potassium hydroxide solution? Okay, so almost the same setup here, right? M1 V1 equals M2 V2, and again, it's asking me what is the new molarity, so we know how we're going to rearrange to solve for M2. And in this case, what do we know? M1 is 0.64 molar. V1 is 35 milliliters. M2 is what we're solving for, and V2 is the original 35 plus the 15 that we add. So again, 50 milliliters. So from here, isolate for M2, so we get M1 V1 over V2. Put in all the numbers I've got, 0.64 molar, 35 milliliters. And then V2 is not 15, but 35 plus 15, 50 milliliters. Okay, 0.64 times 35 divided by 50. We'll call it 0.45 molar. And again, we can visualize that it all makes sense because milliliters cancel milliliters, and we're left with molarity as our final answer. Okay, looks like there's 7 or 8 slides left in this set, so I'll go ahead and stop this video here, and then I'll have one more short video to wrap up this set of slides. So hopefully all these different calculations with molarity are making sense. So one of the key decisions is to figure out, am I using M1V1 equals M2V2, like if I'm diluting a liquid to a lower concentration, or am I using one of those other two example types where I'm dissolving a solid solute into my solution. In that case, right, either it's asking me how many grams of solute do I need to add to make my desired solution, or I have this solution, but the concentration is reported in different units, and I need to convert it. So again, hopefully that's all making pretty good sense.